Hi all, Daniel here. Welcome back to another lecture. We're going to be talking about complexity analysis today. So basically, we're going to talk about how to analyze the running time of an algorithm. Before we start, I'm going to ask you a simple question. I'm going to list a bunch of things, and I want you to have a think about which one of these affect the running time of an algorithm when you run on a computer. Will the CPU of the computer make a difference? You're probably going to say yes, yeah. What about the amount of RAM that a computer has? If one computer has more RAM, we'll be able to run the algorithm faster. What about the memory speed of the computer? Like, let's say you have a different RAM speed, or if one computer is running SSD as opposed to just a normal hard drive, would that make a difference? What about the programming language used? If you write an algorithm using one language and then you write it again using another language, can that make a difference? What about multi-threading versus single threading? What about the size of input? So if you run an algorithm on a small input versus running on a huge input, which one do you think will finish faster? That one may sound obvious, for example. Finally, what about the structure of the input? So imagine that the algorithm has two different inputs. Well, actually, the same input, they have the same size. It's just that they're structured differently. For example, they can be a different order. Would that make a difference on the running time of the algorithm? So hopefully you say yes to all of these, because all of these are factors that can affect the running time of your algorithm. And that actually makes it very hard to properly analyze the running time of an algorithm. So you can't just measure the speed of an algorithm by using a stopwatch. As in, you can't just load up algorithm A in one computer, let it run, and then load up algorithm B on the second computer and let it run and check how much time they take. You can't do that because you can't guarantee that both computers are the same. And even if you load up both algorithms on the same computer, you can't guarantee that they're running the exact same environment, right? You might have different background processes at different times. And you definitely cannot say that an algorithm is better just because you can write it in a different language. For example, if you can write algorithm A in assembly versus writing algorithm B in JavaScript, well, you can't say that A is better. Well, I hope that the assembly one will run faster. And just because the assembly one runs faster, you can't say it's a better algorithm. Just because you wrote an assembly. It's running assembly, of course it's going to be faster. What can you actually? If you can write an algorithm only in that language, only in assembly, is that just a better algorithm? What about if you can write a single-threaded algorithm versus a multi-threaded algorithm for the same problem? Is the multi-threaded one just a better algorithm? So the point I'm trying to make here is that there's just a lot of things to worry about when you're comparing two different algorithms. And we're going to be talking about theory today. We're going to be talking about how, well, actually it's a very simple way to compare two different algorithms. But just understand that in real life, in the real world, there's a lot of things you have to consider when you're comparing the speed of algorithms. For the purposes of Column 3010, we're going to simplify things a lot. So generally, when you compare two algorithms, we're going to strip down a computer to its most basic level. Okay, so let's think about a machine. Let's think about an abstract machine that only has memory, CPU, and input-output. Right? We don't actually have to care about input-output either. Like input-output is just so that we can communicate with the computer. But most importantly, you got the memory and you got the CPU. Now, the speed doesn't actually matter. What matters is what they can do. So memory, you can read and write. CPU, well, it can do the basic operations. So what are these basic operations? So historically, we use a hypothetical symbol computer called the random access machine. The primitive operation of this machine is the addition, subtraction, multiplication, division. You can do function calls, you can do comparisons, and all of these operations will take one time step each. You also have unlimited memory, and you can access memory using just one time step. Well, the memory is arranged in blocks so that if you want to read one memory block, it only takes one time step. So there's a size limit on each block, but you have unlimited number of blocks. The instructions are executed one after another, so you don't have any concurrency. And also loops and subroutines, functions, if you like. They're just composition of the simple operations. So they don't take just one time step. Their complexity is the number of primitive operations within the loop or within the subroutine. If you want to know more about this, you can follow the Wikipedia link there. But generally, in COM 3010, we're not going to worry too much about this random access machine. Just know that it was there. It's very theoretical and very technical. In particular, you probably have heard about the art of computer programming. It's a series of books written by Donald Knuth, and he actually wrote a language. He has this abstract machine called the mixed computer with its own language, which he used to explain algorithms. Which to me was actually the hardest thing about the book. I really couldn't get into it. But that is an example of a random access machine. So basically, it's a theoretical machine that sole purpose is to help you analyze algorithms fairly. What it means here is that if you want to analyze an algorithm, you have to break it down into primitive operations. And then you just count how many operations you need to complete the computation. So this is how you analyze the speed. Now, if you have done subjects like COM 2100, like COM 202, there you've seen a bit of C and assembly, so you probably have a good idea what I'm talking about. You don't actually have to break it down the program into assembly. You can also think about the average Java program that you wrote back in COM 125. I mean, when you're still using primitive operations, right? Or even COM 115. So now the problem with this approach is it fair? Because at least from what you've seen earlier, we're basically just going to ignore multi-threaded algorithms because there's no concurrency, right? So right off the bat, we only care about single-threaded algorithms. Is it realistic? Like one of the primitive operation is multiplication, and we say that both multiplication and addition take the same time step. And obviously that's not the case because multiplication takes longer than addition. Okay, so is it perfect? No, but it allows us to have a nice simple model of our algorithm that we can then analyze. So the idea here is that if with this model, algorithm A is better than algorithm B, then if we then apply both algorithms in the real world, there's a very good chance that algorithm A will be better than algorithm B anyway. Okay, so think of it like it's just a model. Like I have a picture of a wind tunnel there, right? If you're testing modifications on your airplane, you don't actually build an airplane and fly it. You put it inside the wind tunnel and see how it behaves. So is the wind tunnel a exact representation of the real world? No. So the same thing with this random model of computation, the same thing with our approach in theory today. It's not a perfect metric, but it's useful because it's simple, and we can already say a lot of things with this model. So in practice, you really don't have to worry too much about it. Just remember that when you analyze an algorithm, strip away the more complex operation. For example, you when you're sorting, you have to realize that sorting takes some steps. So sorting doesn't take just one time step. When you have a map, like a tree map, and you're trying to find an element inside that tree map, that doesn't take just one time step. What about if you want to compute 2 to the n? Right? That's exponentiation. But if you have done COM 202, you probably know that taking something to the power of 2 is just a bit shift. So in our case, yeah, that will only take one time step. So yeah, we do have the primitive model that only has a certain number of operations. It only has like addition, multiplication, subtraction, division, and we all say they all take one time step. Are we going to follow that exactly? No. For example, we are going to say that multiplication costs more than addition. So it really depends on what we're doing, like what topic we're at. But just one more time, the idea here is that if you have an algorithm to analyze, you have to be able to break it down into small operations, like the primitive operations. And the running time of the algorithm is just the number of operations that is executed by the algorithm. So you need to work out what these primitive operations are. For example, you can look at the CLRS, page 25 to 27, when they're analyzing insertion sort. As you can see there, there's the pseudocode there. And the rightmost column just counts how many times each operation is performed, like n times, n minus 1 times, and so on. And each operation has different costs, C1, C2, C4, up to C8. And if you write down the total number of operations, it gets really complicated, like what you see down there. Right? And this is just insertion sort. Okay, so as you can see from the previous page, or just down there, we normally represent time complexity using the notation Tn. I'm probably just going to say complexity from time to time instead of time complexity. The good news is that you're not going to do something as rigorous as what you saw in the previous slide, right? You're not, or this formula down here, you're not going to be doing something as insane as that. Because in most cases, it's enough to just identify what is the most significant operation, right? And then you can just work out the complexity of the algorithm from there. So from what you can see down there, the most significant term is the n squared. You can see the n squared here. So you can say that this algorithm is n squared. We're going to talk more about this in a bit. All right, but in summary, just want to say that analyzing algorithm can be hard. So we need to use a simplified model where we only care about the primitive operations. And when you analyze an algorithm, what you do is you break it down into primitive operations and just count the number of operations it takes to finish. That's all you do. Right. So we'll move on to complexity notations.